and arrived at our condition that said that for a spontaneous reaction, for a reaction in which delta S of the system plus delta S of the surroundings was in fact increasing greater than 0, that this condition down here was true. That delta H of the system minus T delta S of the system would be less than or equal to 0. Equal in the condition that the reaction is non-spontaneous, that you're at an equilibrium, but less than 0 in the condition that the reaction is spontaneous. If it's greater than 0, the reaction is non-spontaneous. So this equation basically relates the spontaneity to the spontaneity of a reaction to the enthalpy of the system, the change in enthalpy of the system, and the change in the entropy of the system, right? And we defined this new state function, G, that gives free energy, was equal to H minus Ts. And just like our internal energy, our entropy, and our enthalpy state functions, it's a state function, and so the changes in G don't depend on the path taken, they only depend on the initial and final states. That is going to end up being pretty useful for us. So, moving right along. We've seen that the Gibbs free energy is composed of the enthalpy and the entropy state functions, and enthalpy includes internal energy in it. We've seen that internal energy, enthalpy, and entropy are dependent on the variables pressure and temperature, right? If we change the pressure and temperature, then our internal energy and our enthalpy are going to change as well, and our entropy is going to change as well. And so we should expect to find that our Gibbs free energy, the magnitude of the Gibbs free energy, also changes if we change those variables, pressure, temperature, volume. And so what we're going to do right now is we're going to derive really quickly, actually we're going to just review derivation that your book does. We're going to derive the expression that tells us how the Gibbs free energy changes if we are allowing those variables, temperature and pressure, to change. So the question that we're trying to answer is, if the Gibbs free energy of something is, some value at one particular value of temperature and pressure, and then we allow temperature and pressure or pressure to change, what will the Gibbs free energy of that substance be at the new values of temperature and pressure, right? And the way that we're going to do this is kind of long and drawn out. I just wanted to put it up there because you can review in your book. I'm hoping that I'll be able to help you understand it a little bit. If it's not absolutely clear, don't worry about it too much. It's really the end of the result of this derivation that we're most concerned with. And once we get there, we'll try to figure out why that is. So what your book does is it says that if your Gibbs free energy is H minus Ts, and you move to some new condition, maybe you change the temperature, maybe you change the pressure, whatever it is, then the Gibbs free energy will change. And so G equals H minus Ts will turn into G plus dG, so G plus whatever the differential change in G was, is equal to H plus dH minus T plus dt times S plus ds, right? So you're saying move from one state to another, everything changes by just a differential amount. We'll include that differential in there, and then we'll start multiplying across. You can see that you're going to have to multiply T plus dt times S plus ds. When you do that, you're going to get this big term right here where you've got Ts, Tds, SDT, dt ds. And at this point, we can cancel a few things. We see that we have G over here on one side of the equation, but we've also got H plus, or H minus T S right here. So there's minus Ts, H minus Ts. But G is equal to H minus Ts, and so those two terms just go away, right? It's the same thing, you cancel them on both sides of the equation. This dt ds term, those terms are so tiny that differential change in T times differential change in S is going to be an even smaller differential. And so this thing is so small it can kind of be neglected, it goes away. And what we're left with is this expression. dg is dh minus sdt minus tds. And now we've got to figure out that this term still isn't quite where we want it to be. What we're going to take note of is that h is equal to u plus pv. And if we run that same kind of logic that we did back here where we said h is, or g is h plus ts, or g is h plus ts, and we took the differential change in g to get the new expression for g, we can do that same thing with h. We can say h plus dh is equal to u plus du plus p plus dp times v plus dv, right? Because h is u plus pv. And so h plus dh will be u plus du plus p plus dp times v plus dv. We end up with a whole other big term when we multiply these two terms together. And that term contains a u and a pv term. And we've just got an h term over here from the other side. And so h is u plus pv. So again, we've got something showing up on one side of the equation that's also on the other side of the equation. We can cancel it out. We can get rid of that h, the u, and the pv. And now we have that dh is equal to du plus pdv plus vdp plus this term right over here, which is dp dv. And again, this double differential term is so small that it can just go away and leave it. And so what we get is a term that says dh is equal to du plus pdv plus vdp. And we can just substitute that expression for dh into this spot right here. So instead of dh, we have du plus pdv plus vdp. And then we still have the negative sdt and the tds. So this right here, this bottom term, is our new expression for the differential change in g. Don't worry, you're not going to have to derive this. I just want you to see where it came from. So now we're going to take advantage of the fact that g is a state function. Because g is a state function, we can evaluate changes in g along any path that we want, and as long as we've evaluated correctly, that those changes will be appropriate for any path, so for all paths. And so what we're going to do is we're going to say that we're going to evaluate dg along a reversible path, and for a reversible path, we know that ds is dq reversible over t, right? And so tds, this term here, is just dq reversible, right? And then we have that, we have that for work happening reversibly, the internal pressure and the external pressure are identical. And so dW is negative P external dV, which is negative P internal dV, so we just write P dV because we're talking about the P of the system in this case. And, I don't know. And so that gives us a term that we can substitute for the du, right? If du is dq plus dw, and dq is TdS, and dw is negative PdV, then du is TdS minus PdV. So we can just substitute this TdS minus PdV term in for du, and now we have this big long expression here. But you'll notice that the TdS that we got from the du term cancels with the TdS term over here, right? Put the slash through it. The PdV term from the differential of u cancels with the PdV term there. Those two terms go away. And we're left with an expression that says that dg is equal to vdp minus sdt. Yeah? And this isn't the only way to get to this, to arrive at this expression. You can use well, there's a bunch of relationships that we're not going to go into, but there's other ways to arrive at the same conclusion. Suffice to say that this differential allows us to track changes in the Gibbs free energy with respect to changes in pressure and temperature. And it's going to be our go-to equation. Whenever we have the Gibbs free energy in one state and we change to a different state, this expression will allow us, will give us the ability to find out the new Gibbs energy. Go ahead.
What role does the volume play in this equation?
Say that one more time.
What role does the volume play in the equation? Like, does the change in volume affect the? Because it's just.
Well, we're gonna. Hopefully, we'll go through a few examples, and that'll start to clear this up. So let's start working the examples, and hopefully that'll give you kind of an idea for how to work this. So I want you guys to start to try to relate the different math techniques that we've been using to the ones that we're going to be using. You remember with the heat capacity, or with the enthalpy and with the entropy, we had these expressions that said that if we wanted to find out the enthalpy at some second temperature, at some temperature T2, then we take h of T1 and add to it this term, the integral of c sub p dt. We've used that several times in problems. And also we saw that for the entropy, if we were trying to figure out what the entropy was at some new temperature T2, that it would be s of T1 plus the integral of Cp over T dt. We can use this differential form of the Gibbs free energy in a very similar way. And so basically, you'll end up with a condition that says that the Gibbs free energy at some new pressure or some new temperature is equal to the Gibbs free energy at a certain pressure or temperature state, plus the correction term, which ends up being the integral of either VdP or SdT or both. It would be just for a constant temperature process, dt would be 0, and so the VdP term would be the one that you integrated from the initial pressure to the final pressure to figure out what the new Gibbs energy was. If you have a constant pressure process where temperature is changing, then the VdP term goes away, and the term that you integrate for the correction is that negative SdT term. And so you have G of T1 or G plus the integral of negative SdT from T initial to T final. Basically, when you're doing this, we'll look at the pressure-dependent changes. We saw that the pressure depended on the volume. I just got rid of that thing. Put it back up here since it's disappeared. G equals VdP minus SdT. So for pressure-dependent changes, when temperature isn't changing, we've got the volume times the differential change in pressure. For solids and liquids, volume is relatively independent of pressure, and so if you were trying to do this correction, that volume term would be able to come outside of the integral, and then you're just integrating dP, and so integral dP is P evaluated from P final to initial, is P final minus P initial. And so if you have a solid that is at one particular Gibbs free energy, and then it moves on to a new pressure, you want to find out the new Gibbs free energy, multiply the volume of that solid, which is a constant, times the change in the pressure, and that'll give you the correction to your Gibbs energy. For an ideal gas, the volume is not constant. The ideal gas volume changes very, very readily with pressure, and so that V in this case would not be able to come to the outside of the integral like it did over here. It would have to stay in the integral. You just model it as an ideal gas, and so the molar volume of an ideal gas is RT over P, and so you're just integrating 1 over PdP. So your expression will be G of P2 is equal to G of P1 plus RT natural log of P final over P initial, right? Because your volume is the ideal gas volume and it can't come outside of the integral. So, temperature dependent changes. Basically, DG is negative SDT. If you're considering temperature ranges over which the entropy is constant, then the S can come outside of the integral, and your final G ends up looking sort of like the analog for the pressure dependence, where you have S times T final minus T initial plus G of T1. If the S weren't relatively constant over the temperature range of interest, if the entropy wasn't constant, then you wouldn't be able to factor it outside of the integral, and you'd have to have a full expression for the entropy as a function of temperature before you integrate. But for the most case in this class, for most parts in this class, we're just going to be considering situations where the molar entropy can be considered constant over the temperature range. That means the temperature range is going to have to be very small, because we've seen that as temperature increases, so does the entropy. So the entropy wouldn't tend to be constant with temperature, but for the sake of using the math and analyzing problems, we're going to consider it to be constant. So to try to learn how to use this, we'll look at first just the relative stabilities of different phases of a pure substance. So pure substance, we know, can exist in the solid, the liquid, or the gas phases, right? And we're going to try to use that expression, dG is dP minus SdT, to relate the relative stabilities of the solid, liquid, and gas phases with respect to changes in temperature and pressure. Okay? And so these graphs here result from this equation. These are taken, this is Gibbs free energy versus pressure, and so we're assuming the temperature is held constant. We're holding our system at one particular temperature, and we're allowing the pressure to change. The slope of the graph is going to be proportional to the molar volume of the substance, right? This goes away, and we're only talking about dG's dDP. And so the slope of the Gibbs free energy versus pressure curve for solids, liquids, and gases is going to be proportional to the volume. You notice that the gas phase has that arc because the volume is the nRT over V volume, and so nRT over P volume. And so this guy has the largest magnitude. You can also just think in terms of the molar volume of the gas being much larger than the molar volume of the solid, right? And so it tends to be that the liquid has the next largest molar volume, and you'll notice that the slope of the liquid curve then ends up being second in line, second largest magnitude, and the solid tends to have the smallest molar volume, and so its slope has the shallowest curve. When we look at these graphs, we need to understand that whichever species has the lowest Gibbs free energy is going to be the species that is favored at that particular condition of pressure. So this ends up being really cool once we look at it. Increased pressure, which phase, solid, liquid, or gas, based on these curves and the slopes of the curves, is going to end up having the lowest Gibbs free energy. So, right. So the solid has the slowest slope, so its value increases the most slowly with an increased pressure. The increased pressure, and they'll tend to be that the solid ends up having the lowest Gibbs free energy, meaning that it's the most stable state. At low pressure, super low pressure, the gas phase species has the lowest Gibbs free energy. And so if you lower the pressure, the atmospheric pressure around a substance, you end up favoring the gas phase. Well, this kind of makes sense. You learn to think of this as the effects of an outside force on your system. If your system is being pushed on with high pressure, it's going to respond by contracting, right? By getting smaller. And so it turns out that an increase in pressure will end up favoring the phase that has the smallest volume. And that's simply because you push on something, it responds by contracting. So the smallest molar volume is the solid. You increase pressure, you lower the Gibbs free energy of the solid, making it the most favorable state. Or you make it so that the Gibbs free energy of the solid is lower relatively than the liquid or the gas phases. Yeah? Water's a little different. Water's a little different. So water and some of those other substances, remember, a slope's proportional to the molar volumes. Which is larger, the molar volume of liquid water or solid water? Which one's larger, the molar volume of the liquid water or the solid water? Right. Ice is less compact, it's less dense than liquid water, and that's why ice floats, right? And so, due to that, an increase in pressure will actually raise the Gibbs free energy of the solid above that of the liquid, favoring the liquid phase for water and substances that behave like water. The truth is, I only know of water that behaves that way. There's probably other things that do too. What's the other one? H2S, would that work? It's basically got the same structure as water. Possibly, I don't know. So just looking at that first part of the differential, the pressure-dependent term being proportional to the molar volume times the change in pressure, we end up with these graphs that suggest that an increase in pressure favors the most condensed phase, a decreased pressure favors the most dispersed phase. Now we're going to look at temperature. So when we're looking at these graphs, we look essentially from the same perspective, except now you'll notice that the slopes of the curve are negative, and that's because the slopes of the curves are negative, and that's because we've got this negative sign in front of the S, right? And the magnitudes of the curves are, the magnitudes of the slopes are proportional to the sizes of the molar entropy. So in terms of the molar entropy, the molar disorder, which phase, solid, liquid, or gas, has the highest entropy, has the most disorder? Gas. Gas has got the most disorder, and so you'll notice that the gas curve has the largest slope, right? And the solid phase has the least disorder. It has the smallest slope, or the gas has the largest negative slope, the solid has the smallest negative slope, and the liquid is somewhere in between, right? And it gives for energy versus temperature curve. So, looking at those, which phase is going to be favored at high temperature?
Gas.
Right. So the phase with the most disorder and the highest entropy ends up lowering its Gibbs free energy the most when temperature is changed, and so it becomes the most stable phase with high temperature. You go over here to low temperature, and the solid phase ends up having the lowest Gibbs free energy at a low temperature, right? Does that make sense? What happens when we cool something down to a really low temperature? It goes to solid phase, right? So lowering the temperature ends up favoring the solid phase, and raising the temperature ends up favoring the gas phase.
Sorry, I can just make it, I mean, it's just that I can't wrap my mind on it. If you put more temperature into a gas, well, what would drop the energy? Should it be more reactive?
We're just talking about the phases of matter and which ones are the most favored, and whichever phase has the lowest Gibbs free energy is going to be the phase that that's favored at that particular set of temperature and pressure conditions. And so, because the Gibbs free energy of the gas lowers the most with an increase in temperature, because the gas has the largest magnitude of the S value and the slope is negative, because that's the case, if you increase the temperature, you make the relative stabilities of the gas, or you make the relative stability of the gas greater than the stability of the liquid or the solid, because the gas has the lower value of the Gibbs free energy. This is a little weird because we're not really talking about, on a molecular level why this is happening. We'll try to do that. We'll try to do that a little bit more in a second or two. But right now we just kind of have to learn to believe in the equations, and hopefully after using the equations for several problems, we'll start to become comfortable with them. So we looked at, what we're going to do right now is we're going to just make some observations using the Gibbs energy versus temperature curves. That's the curve that we just looked at. We're going to redraw it, and then we're going to ask ourselves the question. So remember I told you that these curves were taken holding the other variable constant. So the Gibbs energy versus temperature curve was plotted holding pressure constant. Now we're just going to plot two of these curves on top of each other. One at P1 and one at P2, where P2 is larger than P1. So we're going to increase the pressure. I should have stated that we've actually increased the pressure. I didn't write it on the notes. Maybe next year, if I'm still teaching. We're basically just plotting these two curves on top of each other. Remember that a change of pressure goes as the magnitude of the molar volume. And so if we take a curve at a new value of pressure, the Gibbs energy of the gas is going to increase the greatest. And so you can imagine that curve just repositioning itself, and there'll be a difference between the initial curve and the final curve that's Vm dp, right? But the magnitude of Vm for a gas is larger than that for a solid or liquid, and so the shift of that gas curve is going to be the greatest in magnitude. It tends to be that the molar volume of the solid is less than the molar volume of the liquid, and so there'll be an increase there'll be a shift in the curve for both the solid and the liquid, an increase in the Gibbs free energy, but the shift of the liquid will tend to be larger than that of the solid. And we just want to point out what the result of this has been. These points where the two curves cross, those are the points where the Gibbs free energy of the two phases are equivalent, they're equal. And so the place where the Gibbs free energy of the solid and liquid are equal is the place where melting occurs, right? That's the melting point temperature. The solid goes to liquid reversibly at the melting point temperature. We notice that when we shift these curves by shifting the pressure, the melting point Tm2, where the two curves intersect in the second set of graphs, is at a larger temperature than it was back here. It's shifted over to the right on the axis. And so an increase in the pressure, according to this, will increase the temperature at which a substance melts, right? That makes sense because melting is defined as the point that a substance overcomes its intermolecular interactions that are trapping it into the solid phase, and it's able to break free and go into the liquid phase, right? And so a high pressure will tend to hold something in the solid phase as long as it's not water. You push down on something, then those molecules are going to try to stay, it's going to act to keep them attached to each other in that condensed phase. Raise the pressure from one pressure to a new higher pressure, and essentially there's greater forces acting to bind that substance into the solid phase, and so if you want to get it to melt, you're going to have to bring it up to higher temperature, right? And so an increase in your pressure will shift that melting point temperature. Similarly, this point right here is the boiling point. It's the point where gas and gas and liquid. I messed that up. I labeled the gas. This is what happens when I'm in a rush. This should have been